last day of 2.1. I'm going to assume that you have watched all the 2.1 videos. You're going to have most of this period to work on your 2.1 homework. If you get done, you can start the 2.2 stuff. You can watch the videos, you can do the homework. The next 2 days are 2.2. I have, however, already discovered one mild problem with my calculator, or with my schedule that I gave you guys, which is that I wrote 2.1/2.2 quiz for this weekend. I don't know that I'm comfortable with that, because we're going to do 2.2 Thursday and Friday, and then you walk out the door and we're done with 2.2, and I give you a quiz without giving you time to think about it, reflect on it. So I think what I'm going to do this weekend, I'm just going to assign you the 2.1 quiz, and I may next week give you a combined quiz that'll have some 2.2 questions and some 2.3 questions. So I'll figure that out before next week. But the quiz this week, which will open Friday when school ends, you've got all weekend to do it. It's due before you walk into class on Monday. It's on formative. There's a link in Google Classroom. When you're done, I ask that you click done in Google Classroom. It actually helps me to grade. If you don't click done, then it makes grading for me harder, because then it splits it up into weirdnesses. So there's a couple things I want to just quickly touch on out of 2.1, and then I will open it up for questions, and then you will have the rest of the period to work. I'm going to try to do this every section and just have some quick comments at the end before I let you ask questions. Things that I'm sure I touched on in the videos, but I just find that sometimes it's helpful to have things emphasized so that you know walking out what I think is important. So here's sort of my recap of 2.1. Average speed, which is my change in my y value divided by change in time. Pretty basic. I went 10 miles. It took me 1 hour. I averaged 10 miles per hour. Instantaneous. Oh, and another way to write this would be, where was I at B subtracted by where was I at A? So in other words, if I start at A and I go to B, that's how far I went, divided by my change in time. Instantaneous speed is sort of the first time we start to really think about calculus, because instantaneous speed, I have to have 2 points to calculate speed. I mean, how fast am I going right this second? Okay, well, I'm not moving, but how fast am I going right now is a little bit trickier than how fast did I go on average over the course of the hour. Now, your speedometer tells you instantaneous speed. But if you don't have a speedometer, well, then what do? You just got some function. And so what we do is we say, well, instead of I start at A and I end at B, and my average speed is just calculated using that line, agreed, change in Y over change in X. I'm going to change this up a little bit. I'm going to get a pen that writes darker. I'm hitting that one. I'm going to change this up a little bit, and I'm going to say, well, I'm starting at A, and I'm ending at A plus H. This distance right here is H. Average speed then becomes my change in distance divided by my change in time. Agreed? Mm-hmm. Well, except that my change in time in this case is just H. There's f of A There's f of a plus h. I take the change in my y value divided by the change in my x value. This is my average speed over that interval. And this is where limits become so important. Because what if I make the interval smaller? If I drive for 2 hours, I could divide by 2. Okay, well, let's say I drive for 1 hour. Now I divide by 1. More accurate, agreed? Because it's a smaller interval. What if I say, how far did I drive during this minute? Oh, well, that gives me a pretty accurate, right around this little minute from here to there, I was going that fast. Well, what if I say, how about for 1 second? I'm driving down the road, and I'm here, and then I'm here. Okay, that's pretty accurate for how fast was I going during that second. What if I say 1/10 of a second? Or 100th of a second? Or 1/1000th of a second? Or what if I say, what if I take the limit of this as my time interval goes to 0? So now I'm just looking at that function and saying, okay, well, what if h goes to 0? Now, can h be equal to 0? No. Look at the equation. If h is 0, I'm dividing by 0. Not allowed to do that. Oh, and if h is equal to 0, then that's f of a minus f of a, which is equal to 0. So if h is equal to 0, then I've got 0 divided by 0, which doesn't tell me anything. And this, again, goes back to that idea of limits. That limits are not where you are, it's where you think you're going to be. You can't actually do this calculation for an interval of 0. But you can make that interval so small that it looks like you're getting to 0. And there's your instantaneous speed. Now, that's the easy part. Because the hard part is these functions get complicated. But that's the moving on part. That's now you got the basic idea. You need to know how to calculate average speed. You need to know how to calculate instantaneous speed. At the least, you need to know those two formulas. Let's change this to E minus A. You need to know that formula. You need to know this formula. Moving forward, be aware. Quizzes are going to be just open book. You're taking them at home. You can use any resources you want. I'm going to ask you not to just go on the internet and look stuff up, but you can use your notes and quizzes. You've only got 30 minutes on each of the quizzes. They get a little bit longer later in the year if they get a little bit more complicated. You need a bit more time to process. So bear in mind that you won't have time to, with 30 minutes and 5 questions, they're true, false, multiple choice. But with 30 minutes and 5 questions, you don't have time to just sit and figure them all out by flipping through your notes trying to find something that looks similar. You need to know the stuff, but I'm going to let you use the notes because why not? The purpose of the quizzes is to get you comfortable with what kinds of questions are going to come up from each section. Okay? When it comes to tests, I'm going to let you have a note card. You put anything you want on it. Okay? You'll have one note card. You can make a new one for each task where you take off stuff that you know and add stuff you want a little help with. Some things will become obvious after a while, like the formula for average speed. So maybe then for the further future chapters, you take that off because I know that one. Don't need to waste time on my note card. Okay. I'm also going to give you some sheets, and I haven't made them up yet, but now we got some formulas. I probably will give them to you tomorrow. I've got some blue sheets that are just formulas and things I need to know so that you can fill them out as you go along and have one reference instead of having to flip through your notes trying to find all those things. I'll give you those tomorrow. All right. Okay. Properties of limits. There's a table properties of limits. It's a good idea to know those because it makes life easier. If I ask you what the limit is as x goes to 0 of x squared, presumably you'd all say, well, that's 0. If I ask you the limit as x goes to 0 of 1 over x, you would say, well, that's infinite. But if I ask you what the limit of x squared plus 1 over x is as x goes to 0, it's useful to know that one of the properties of limit says I could look at that, and I could look at that, and then I can just add them together. So it's 0 plus infinity, so this one is infinite. As opposed to trying to think of x squared plus 1 over x as one function, and what does it do? So that little table of properties of limits, probably worth copying down in your notes if you haven't. Along the hallways during my calculus class. Left hand and right hand limits. I want to talk very briefly about those because the notation, by the way, this diagram is a beautiful diagram that you should just totally have if you don't already. Because that diagram, I think, explains so awesomely the concepts of average speed and instantaneous speed. Anyone need this? Can I erase this? Over here? Yeah? Okay. Got to be quick. You don't want me to erase stuff. You got to say, oh, wait, and I will stop. It's too late now. All right, left hand and right hand limits, handed limits. Here's your function. Here's your point. The limit as x approaches c from below. That's what that means, from below. That means from the left. It does not mean from down here going up. It means from down here going up. Okay? So that's this right here. And if I were to draw a different function in purple, looking like this, that's still the limit as x approaches c from below. Do not be confused. Below means to the left on our number line. This is a left hand limit because you are coming from the left. Okay. On this side, the limit as x approaches c from above. That means from above that you are coming this way or that way, from above on a number line, not from above in a vertical sense. This is a right hand limit. Okay. Final thing you need to know is that the limit as x approaches c exists if and only if. There's notation you've probably never seen before. This means if and only if. It's a very exclusive meaning. If I say if, okay, that could mean there's a lot of wiggle room in an if. but this says can't exist otherwise. Okay? You'll see this a lot in math moving forward. You won't see it so much in engineering, but it's probably going to take a lot of math to get to engineering. You're going to see this a lot. That limit exists only if the left-hand limit is equal to the right-hand limit. So you calculate that this goes to 2. Let's say that that's 2. And you calculate that that one is going to 2. Well, then the limit is 2. Because they both go to 2. Bernie and Betty, the bugs, think they're going to meet at 2. Therefore, the limit exists. It does not exist if they're different. That limit does not exist because the left hand is 2 and the right hand is 2.5. Bernie and Betty do not think that they're going to meet. Bernie's headed here, Betty's headed there. Limit does not exist. The left-hand limit exists, 2. The right-hand limit exists, 2.5. But the limit at that point does not exist because they have to be equal for there to be a limit. All right? Any questions? Any questions on the homework that you've been working on?
Well, it's more general. What are we doing today? Are we doing all of the exercises?
All of them, yes. 1 through 80. No, you're working on the homework, the assignment I gave you.
Oh, okay.
If you're done with 2.1, you can move on to 2.2. All right? Any problems that you want me to go over that you've been working on? By the way, I put the 2.1 keys up on Google Classroom. You may notice that some of the problems in my key I didn't assign you. And that's because I made the keys my first year. And then when I changed the homework, I really don't feel like rewriting the whole key. So I just sort of like, oh, well, there's one I didn't ask them to do. They'll look at it and go, oh, he didn't ask me to do that one. Skyler.
Can you do number 36?
36. Use a graph to explore whether the limit exists.
Never mind. That's not the one that I saw.
Hey, let me talk about that though. Let me talk about the basic idea there. Guys, you don't know how to find the limit to that equation. That expression, x plus 1 over x squared minus 4, you don't know how to find that. Or maybe you do. But let's assume for the sake of argument that you don't know how to find this one. Well, one way to do this is to just draw a graph. And thankfully, we've got technology that allows us to easily draw a graph. And so then what I do is I go into my graphing calculator and I say, okay, well, there's x equals 2. What happens there? And then what I see is that from one side, the left-hand limit is going to be something or other, and the right-hand limit is going to be something or other. And if they're equal, then that's the limit. And if they aren't, then the limit doesn't exist. But graphically is a really, really good way to find limits for things that you just don't know how to deal with algebraically. That one's actually fairly simple algebraically, because I could just say, well, what happens if I put in 1.99, which is on the left-hand side, and what happens if I put in 2.01, which is on the right-hand side, and I can see what happens. But there's ones that we'll see later on. For example, what's the limit of that? Sine of 0, 0. X is 0. I don't know what the limit of that is. And I don't know how to calculate it. But I can look at a graph and I can see, oh yeah, look, I see it doing something. Okay? So I'm glad you said that, even though that wasn't the one you intended, but it worked out for the best.
Well, now I can't find the one that I was gonna
Okay.
say.
Hey, suggestion, and then I'm gonna, Harry, then I'm gonna ask you your question. As you're working through your homework, if you got one that's got a question, take an orange highlighter and just put a blob next to it so that you don't have to dig through trying to figure out, oh, I know I had a question and I can't remember what it was. Harry.
Can you explain 44 H?
H, the limit exists. True or false? The limit exists at every value of C in the interval -1 to 1. The limit exists in every C in -1 to 1. All right, let's look at the graph. -1. 1. Pick a value. Walk along the curve. Are they the same on both sides of the value you picked? We agree true everywhere, except question is what happens at the ends. Agreed? This is a continuous function, so if I pick any random point, the bugs are going to meet. The limit, as I approach that random point from below, is equal to the limit as I approach that random point from above. Yes? So the only question is, well, what about here and here? Could I say that a limit doesn't exist just because the function stops? And the answer is no, there's still a limit there, but I just ignore the one that's not part of the function. I get to ignore the right-hand limit over here because there isn't a right-hand limit. Not infinite, it just doesn't exist because the function doesn't exist over there. So I get to say that, well, I've got a limit coming from this direction. Oh, okay. The limit exists because there's nothing to compare it to. Otherwise, no function that ended would ever have limits throughout the function. And then same thing on the other end. That make sense? Does that answer your question?
Yeah.
Cool. What else?
So that's like nothing, but as it's a point of the graph, but they're just two numbers between.
Interval.
Yeah.
Actually, let me expand on this a little bit further because I didn't look at the interval carefully. That interval means doesn't include the endpoints. This interval means includes the endpoints. This includes 1. If I was going to write this as an inequality, I would say -1 less or equal to x less or equal to 1. If I was going to write this as an inequality, I would say -1 less than x less than 1. So that actually makes it even easier as far as do the limits exist, because I'm not counting that point right there, which means that no matter how close I go to that point, there's always going to be something on the other side to make that limit. I could go to 0.9999999999999, and say, oh, well, I got a left and I got a right. So I didn't even have to think about one-sided limits, which I'm not sure if we've talked about one-sided limits in 2.1. Or if that doesn't come till 2.2, which may be where the confusion stemmed. You comfortable with this? Something else occurs to me. Did everybody understand that that was an interval, not a point? That was the confusion. Thought that that was the point -1, 1, which is, yeah, that's just a point on the graph as opposed to, yeah. No, that's, so here's the key. If you see at, this means it's a point. If you see in or sometimes on, usually you'll say on the interval and it'd be more explicit. But if you just say in and then have the interval notation, it just means, yeah, we're in that interval. Okay? Little things that just, as somebody who's been doing math forever and ever and ever, you just assume. Cool, what else? More questions? Problems you want to look at before I let you go? Harry?
For H of that one?
Yes?
Would that be false because there's the, or like a little.
If it was the other one.
Well, we won't talk about if it was the other one yet. Because it doesn't matter for the purposes of this because they haven't talked about, I'm pretty sure they have not, we have not talked about one-sided limits yet.
You didn't talk about
Now, you're right, but they don't really either yet. They talk about one-sided and two-sided limits. So the question of does the limit exist if your function just ends? And the answer would be, well, yeah, the limit exists because you're going there. And, you know, you're going to get closer and closer and closer to that point. And what's happening over here is sort of irrelevant. You still think you're going to get to that point. I still think I'm going to get to the point 1, 2. Now, is there the love of my life waiting for me on the other side? No, because there is no other side. That's a limit where I would just get there and be lonely forever. But I still think I'm going to get there. I'm going to get to eternal loneliness.
That's just getting depressing.
I know. It's such an awesome analogy. All right, but yeah, don't worry too much about does the limit exist if it's a one-sided limit because the function stops, because that's beyond the scope, in my opinion, of section 2.1. And as long as it's an open interval, then it doesn't matter because you're never actually getting there anyway. You're just getting closer and closer. There's always something on the other side. There was a hand. Yeah, well.
what does int x mean?
Int x. Oh,
Number 12. limit
yeah.
of x approaches
Yeah, good. It's the floor function. It's funny, this book assumes everybody knows that function. Even all the years I taught pre-calc, we'd never, ever, ever discuss that function. And they just dive right in, assuming that you all know the function. Int x. Sometimes written like, I think it's that. This is called the floor function. And here's what it does. Round the nearest lower whole number. You know what? Let's do this. Round down the nearest whole number. Int of 1.5 is 1. Int of 0.3 is 0. Actually, technically it's This is why I couldn't have been a math major. I had to be an engineer. Because whole numbers don't count in negatives. Round down to the nearest integer. Stupid difference between integers and whole numbers. I hate them. Why do we need two words? Come on now. INT of negative 0.5, negative 1. You just move down to the next integer.
So,
Yes?
int of 0.5 would be 0.
Yes.
Okay.
And if you want to look at it in your calculator, it's in there, math menu. It's sort of a cool graph because no matter what the x value is, the y value is always a whole number. So the graph of this looks like it's actually super useful. I mean, think about the problem that you saw way back in probably algebra. How many buses do you need to carry students to the football game? If a bus carries 60 people, everything from 0 to 60 is 1. Everything from 61 to 120 is 2, and so on. Where you can very easily write a mathematical equation using the floor function by just saying, in that case, 60 times intx, because it will then just round. Or you might have to be 60 intx plus 1 or something like that. You got to fiddle with it to get it to be the right equation. But it just makes your number into some integer. So you want to know how many buses to take? You're not going to get a decimal and then have to look at it and go, okay, what I got to round that? What do I round it to? 3.78 buses. What?
Yeah, maybe.
More questions? We good? Okay. Rest of the time is yours. Did we all find ourselves headphones? Are we all not bringing our ice cream into my room?
There's no ice cream. It's a cup.
Cup full of what?
Spoon.
Okay. Because if it gets knocked on my floor and now I got Oreo cookie sandwich goo all in my nice clean carpet, I'm going to be very annoyed. Yeah, please don't bring in anything but water, guys. I trust you, but if I make a general rule, then I don't have to worry about it. Plus, my trust is sometimes misplaced. I think you're responsible, then it turns out you aren't. Not a big public coffee on my foot. Somebody did that last year. They snuck their coffee in because they really wanted their coffee, and then they kicked it over because they were hiding it on the floor. And then they snuck out without telling me. So then the next class comes in and it's like, hey, Mr. Harmon, there's like a big puddle of coffee on the floor.
Oh. Oh.
All right,
Use the bathroom.
you may. Sign in and out if you would. There's a sign out sheet there. All right, guys, it's all you. Work, be productive, learn something, graduate, pay taxes,
I don't know about that last one.
pay my Social Security.
I don't know about those last
I don't know how to do the last one.
Honestly, I'm not counting on Social Security, so if you don't work and pay taxes and pay my Social Security, I'll be fine. I've been spent most of my life assuming that the government will at some point run out of money and renege. Doesn't bother me. I would have opted out of the system when I was 20 if they would have let me. You never pay taxes for Social Security and we'll never give you a penny after you retire. I'm in. Yes. You're not gonna be disruptive, are you?
I don't think so.
Okay.
I'll try not to mess with Oreo stuff anymore.
Okay. I'm just adding the link, by the way, to the 2.2 videos into Classroom, because I realized I forgot to.